Hello, everyone. This is Zijun, and today we're diving into the architecture of the No Summary Chat, which is a ephemeral RAD pipeline that I've created in summer 2025. The core object of this project was to engineer a highly secure, low latency retrieval-augmented generation system capable of summarizing and querying personal notes directly from Google Drive and PDFs. Um, Critically, we achieved this without relying on any persistent server-side storage. Our underlying tech stack is powered by a Next.js orchestration layer using Gemini 2.5 Flash model and a text embedding zero zero 004 model for high dimensional vector generation. Right, so this is the high level architect, and this is the basically high level of the data journey. The flow initiates with user input from either a drive or PDF, passing into our Next.js API for dynamic chunking. From there, we hit the Gemini embedded zero zero 004 model, processing the arrays through a in-memory cosine simulation function. Um, then we route the optimal context to Gemini 2.5 Flash, and finally deliver the payload back to the client UI. So architecturally, we made a decision to pivot to a unified serverless Next.js architecture instead of a like bypassing a traditional dedicated Python backend utilizing Flask API with Flask. The operational win here is pretty massive. It drastically reduces our deployment complexity and achieves a near zero cross-origin latency. However, this introduces trade-offs um, regarding the compute cost. We are bounded by the strict serverless timeout limits, ranging from 10 to 20 seconds, because we are deploying ourselves alongside rigid memory caps. So consequently, large PDFs would require a more aggressive size limiting or custom stream architectures. To so these versatile constraints, we engineered a technical workaround um, using stateless Next.js API routes that force temporary persistence through global dis.pdf memory and a fs write file sync endpoint. Furthermore, we instituted a hard boundary through a formidable capping ingestions of 31 megabyte, which I can change um, to whatever I want to like avoid abuse. Alright, moving to the ingestion layer, our stack is locked down using the OAuth 2.0 drive scopes, formidable PDF streaming, and a zero trace memory processing. We made the decision to build entirely stateless rack environments. This means that we process documents entirely in memory, completely um, omitting persistent like S3 buckets or external vector databases like Pinecone from our topology. The primary win here is the maximum data privacy, which I put in the priority for this project. Because no files are stored on our servers, we essentially eliminated all like data governance and lifecycle cleanup overhead. But again, this statelessness comes with a massive compute cost. The trade-off is that any follow-up queries execute a closed session will natively trigger a full refetch, like a reparse and a re-embed cycle, simply because no persistent vector cache exists to pull from. So again, this project mainly focuses on privacy of the user documents over like the exact speeds. Um, so this is the Google Doc ingestion pipeline. So uh, this is a technical flow of our Google Docs ingestion pipeline. It starts with a secure session injection using a Next.js JWT token. This token authorizes our client-side Google Pickers and OAuth Scope UI selection tool. From there, this payload hits our REST API and executes a AEST traversal to convert the raw JSON into clean text. We chose native drive-in integration rather than relying on like heavy third-party parsing libraries because it significantly um, reduces our bundle size and allow us for direct unembedded stream straight into our LM pipelines. If you look at the so inside the code next.js, we customize our JWT callbacks into uh, the we customize our JWT callbacks to dynamically inject the access token into our um, client session, which flawlessly handles the JPI authorization. Meanwhile, in index.tstx, we engineered a extract text from Google Doc function to traverse the highly nested JSON ASC. So it will successfully identify discrete paragraph elements and isolate the raw text strings for processing. All right, so this is the heart engine of our vector pipeline. We take the large ingested document and slice them into 200 tokens chunks, and these are parts passed into the text embedded 004 for vector generation, um, scored through cosine similarity, and outputted through a context retrieval. So the decision here was to implement semantic chunking utilizing a strict 200 token window patterned with some semantic overlap to strictly maintain context. This tight window gives us a high granularity of context um, retrieval and actively prevents the model from hallucination. Um, when prevents model from hallucination when navigating dense technical nodes, it ensures absolutely no detail is lost within the large monolithic text block. The corresponding cost of this micro chunking is a substantially higher APR call volume. Um, Generating smaller chunks natively increases our indexing latency and drastically spikes our API cost when compared to a macro chunking strategy. Once we have these vectors, we filter them with a top five, um, the top five, or more generally top K, with k being the number I chose, which is five. Chunk top five chunk filtering mechanism to finalize contextual retrieval. Um, so inside summarize.ts, we handle pre-processing through a pre-process chunks function. Here, the engine utilizes a custom reg, re, re, regex path to aggressively strip all punctuations and um, non-alphanumerical noise from text segments prior to uh, making embedding calls. And therefore, it's vector normalization. We utilize mod embedding with basically a post generation. The high dimensional vector values were manually scaled by vector zero point 0.9 to effectively normalize the signal intensity across our dense documents. Mathematically, our cosine function calculates the dot product through a array reduce function and divides that by the square root normalization of both vectors, calculating the exact geometric similarities in high dimensional spaces. Now regarding the inference engine, we uh, well, I benchmark the time to first token or TTFT across multiple leading models. Um, well, these were the leading models in summer 2025, which is being Gemini 2.5 Flash, Gemini 2.5 Pro, and GPT 4.0, which you can see the time here. So based on this data, I selected Gemini 2.5 Flash as our primary LM to power our real-time conversational summaries and instant Q&A sessions. Um, the win here is basically a sub-second TTFT yields a high snappy UI, high-speed string responsiveness, and it remains highly cost-effective at scale. Trade-off, however, is reasoning depth. So while Flash is blindingly fast, its accurate fastest some of the deep multi-step logical reasoning abilities compared to the pro tiers. The the real world impact would just be that if a user uploads a 50-page complex legal document, Flash might struggle to synthesize and connect abstract concepts across the entire corpus as effectively as a heavier model would. So to maximize the output quality of the Flash model, we rely on a dynamic prompting architecture. So in ask.ts and summarize.ts, the engine dynamically constructs the LLM system prompt on the fly, directly leveraging the exact user preference. We map configurations such as pref star length equals detailed to highly specific instruction strings. We also actively inject doc-type variables directly into the prompt payload, which acts as a contextual anchor for the model, ensuring high precision domain-specific outputs. Um, so finally, here is the state management. We opted for a client-first config utilizing local storage, persisting within use user context.js by pushing session state, user configuration, and robust telemetry strictly to the browser through local storage. We completely bypass the need for a backend database. Uh, You can see this in action through the like custom hooks right here. The architectural win is that there's zero database maintenance, zero persistent infra costs, instant load times for all user preference, and completely localized client-side session tracking. The only notable trade-off is that it lacks like a cross-device synchronization. So if a user customizes the summarization prompts on their laptop, those settings and locals history will not be synced to their mobile devices or a alternative browser. But given our privacy first mandates, this is an acceptable and highly secure trade-off. So yeah, this is just the information, and now we're gonna head to the demo. All right, here is the app, and if you want to try it out yourself, here's the URL. Here's a kind of summary about the app. Um, so during stress tests, I was able to get the app working with pages over 1,000. But because the enormous size of that file, it did take some time. So I'm not gonna do that for this video, or else it will take too long. So I'll just test on this one, which is some research paper I found, which is like about 30 pages and 15 pages. So we can like just summarize it. And then here's a summarization based on what the user put for preferences. So that was short, simple, and general.